From ancient civilizations to modern science, humanity has long known that our planet is a sphere. But in this video, we're going to take you on a journey through compelling evidence, fascinating experiments, and natural phenomena that all point to one undeniable fact: the Earth is round. We'll explore how different constellations are visible from various parts of the world, the influence of the Coriolis effect on weather patterns, and much more. Whether you're a curious mind or a dedicated truth seeker, stick around as we unravel the mysteries of our beautiful spherical planet. Leave a like and subscribe to support our channel. The belief in a spherical Earth has deep historical roots, with evidence dating back to ancient civilizations. One of the earliest recorded proponents of a round Earth was the ancient Greek philosopher Pythagoras, around the 6th century BCE. Pythagoras and his followers observed that the moon and other celestial bodies were spherical, leading them to deduce that the Earth must be spherical as well. This early notion set the stage for later, more concrete evidence. Aristotle, another Greek philosopher in the 4th century BCE, provided some of the most compelling early arguments for a spherical Earth. He noted that during a lunar eclipse, the shadow of the Earth on the moon is always round, which would only be possible if the Earth were spherical. Aristotle also observed that travelers heading south could see stars that were not visible in Greece, indicating that the Earth's surface curves downward as one moves away from the equator. These observations strengthened the argument for a spherical Earth and were widely accepted among educated Greeks. A more precise demonstration came from the Greek mathematician Eratosthenes around 240 BCE. Eratosthenes measured the angles of shadows in two different locations, Syene, modern-day Aswan, and Alexandria, on the same day of the year. He found that in Syene, the sun was directly overhead, casting no shadow, while in Alexandria, it cast a measurable shadow. Using geometry, Eratosthenes calculated the Earth's circumference with remarkable accuracy for his time. This experiment not only confirmed the Earth's roundness, but also provided a fairly accurate estimate of its size. In the Roman period, the geographer Ptolemy further solidified the understanding of a spherical Earth through his work in geography and astronomy. His book, Geographia, included maps based on a curved Earth and was widely used for centuries. The idea of a spherical Earth continued to be the prevailing view throughout the Middle Ages, despite occasional resistance from flat Earth proponents. The age of exploration in the 15th and 16th centuries provided even more tangible evidence. When Ferdinand Magellan's expedition successfully circumnavigated the globe between 1519 and 1522, it provided incontrovertible proof that the Earth was not only round, but could be navigated in a full circle. This journey demonstrated the practical implications of a spherical Earth and silenced many remaining skeptics. In addition to these historical accounts, various other cultures also contributed to the understanding of the Earth's shape. Ancient Indian, Islamic, and Chinese scholars made significant contributions to astronomy and geography, often supporting the notion of a spherical Earth through their observations and calculations. For example, the ancient Indian astronomer Aryabhata in the 5th century CE described the Earth as spinning on its axis and orbiting the Sun, which aligns with a spherical Earth model. Throughout history, the concept of a spherical Earth has been supported by a combination of observational evidence, mathematical calculations, and practical demonstrations. From the ancient Greeks to the explorers of the Renaissance, humanity's understanding of the Earth has continually evolved, leading to our modern acceptance of its round shape. This journey through history not only underscores the importance of scientific inquiry and observation, but also highlights the enduring power of human curiosity and the quest for knowledge. The scientific community has amassed an overwhelming body of evidence supporting the fact that the Earth is a sphere. This proof comes from a variety of disciplines, including astronomy, physics, and geology, each contributing critical data and observations that collectively confirm our planet's round shape. One of the most straightforward pieces of evidence comes from astronomy. Since ancient times, astronomers have observed the night sky and noted that other celestial bodies, such as the moon and the planets, appear as spheres. This led to the logical inference that Earth, too, would be spherical. More recently, space exploration has provided undeniable proof. Photographs of Earth taken from space show a round planet. Satellites orbiting the Earth provide continuous images that depict its curvature, and astronauts aboard the International Space Station witness the Earth's roundness firsthand. Physical principles, particularly those involving gravity, also support the spherical nature of Earth. Gravity pulls matter toward a central point, creating a shape with the least surface area for a given volume, a sphere. If the Earth were flat, gravity would behave inconsistently, pulling objects toward the center of the disk, resulting in observable anomalies in weight and movement that we simply do not experience. The consistent downward pull of gravity everywhere on Earth further supports its round shape. Navigation and travel offer additional proof. For instance, the phenomenon of the horizon is a result of Earth's curvature. As ships sail away, they appear to sink into the sea, hull first, because the Earth's surface curves downward. Similarly, during an airplane flight, one can see the curvature of the Earth from high altitudes. Flight routes also provide evidence. Planes often travel along great circle routes, which are the shortest paths between 2 points on a sphere. These routes appear curved on a flat map, but are straight on a spherical surface. The concept of time zones is another critical piece of evidence. Earth's rotation causes different parts of the world to experience daylight and nighttime at different times. If the Earth were flat, the sun would rise and set simultaneously everywhere, which contradicts our everyday experience of time zones. Geological evidence also supports a spherical Earth. Earth's shape is more accurately described as an oblate spheroid, meaning it is slightly flattened at the poles and bulging at the equator due to its rotation. This shape affects phenomena like the distribution of Earth's gravitational field, which has been measured and confirmed by satellites and other instruments. Moreover, modern technology, such as GPS, relies on a spherical Earth model. GPS systems use satellites that orbit the Earth, calculating positions based on the curvature of the planet. If the Earth were not spherical, these systems would not function correctly. The evidence for a spherical Earth is vast and comes from various scientific fields. Observations from astronomy, principles of physics, navigational practices, geological measurements, and modern technology all converge to confirm that the Earth is round. This consensus is not based on a single piece of evidence, but rather a comprehensive collection of data and observations that collectively provide irrefutable proof of Earth's shape. The scientific method, with its emphasis on evidence and repeatability, has consistently demonstrated the reality of a spherical Earth, leaving no doubt about this fundamental aspect of our planet. Natural phenomena provide powerful and compelling evidence that the Earth is not flat. Among these phenomena, the visibility of different constellations from various parts of the world and the Coriolis effect on weather patterns and ocean currents are particularly convincing. When we look up at the night sky, we see a canvas filled with stars that form distinct patterns known as constellations. One of the most telling pieces of evidence for a spherical Earth is that different constellations are visible from different locations on the planet. For instance, the constellation of the Southern Cross, Crux, is always visible in the southern hemisphere, but never seen from northern latitudes. Conversely, constellations like Ursa Major are visible in the northern hemisphere, but not from the southernmost regions. If the Earth were flat, one would expect to see the same sky and the same constellations from any point on the planet, assuming an unobstructed view. However, because the Earth is spherical, as one travels from the northern hemisphere to the southern hemisphere, the visible constellations change due to the curvature of the Earth. This phenomenon occurs because observers in different hemispheres are looking out from different angles into space. This shift in visible constellations is a direct consequence of the Earth's spherical shape and curvature. Another compelling natural phenomenon that illustrates the Earth's roundness is the Coriolis effect. This effect, caused by the Earth's rotation, significantly influences weather patterns and ocean currents. The Coriolis effect causes moving air and water to turn and twist relative to Earth's surface, which would not happen if the Earth were flat. In the northern hemisphere, the Coriolis effect causes moving air to deflect to the right, while in the southern hemisphere, it deflects to the left. This deflection is responsible for the rotation of large-scale weather systems, such as cyclones, which rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. On a flat Earth, such a consistent pattern of deflection and rotation would be inexplicable. Moreover, the Coriolis effect also influences ocean currents. For example, the Gulf Stream in the North Atlantic flows from the Gulf of Mexico up along the east coast of the United States and across the Atlantic to Europe. This current, and others like it, are driven by the interaction of wind, water, and Earth's rotation. The Coriolis effect ensures that these currents follow predictable paths, contributing to climate and weather patterns globally. The understanding of the Coriolis effect dates back to the 19th century, with significant contributions from scientists like Gaspard Gustave de Coriolis. This effect has been studied and observed in meteorology and oceanography, providing robust evidence of Earth's rotation and consequently its spherical shape. Throughout history, numerous measurements and experiments have been conducted to understand the shape of our planet. Two particularly compelling pieces of evidence that prove the Earth is not flat are the use of gyroscopes in modern navigation and the Bedford Level experiment, which, despite its controversial beginnings, ultimately confirmed Earth's curvature. Gyroscopes are devices used to measure and maintain orientation based on the principles of angular momentum. They are crucial in modern navigation systems, including those used in airplanes and ships. The way gyroscopes operate provides significant evidence of Earth's curvature and rotation. When a gyroscope is set spinning, it maintains its orientation regardless of the motion of its base. This stability is due to the conservation of angular momentum. However, as planes and ships travel long distances, gyroscopes must adjust for the Earth's curvature and rotation. For instance, if an airplane flies from one point to another over a long distance, its gyroscopic instruments must account for the fact that the Earth is not flat, but a sphere. This adjustment is necessary to maintain accurate navigation. If the Earth were flat, there would be no need for such adjustments, as there would be no curvature to account for. Additionally, the Coriolis effect, which causes moving objects to follow curved paths due to Earth's rotation, is factored into navigation systems. This effect further reinforces the spherical nature of our planet. The Bedford Level experiment, conducted in the 19th century, is a fascinating case study in the scientific method and the pursuit of truth. Initially, this experiment was used by flat Earth proponents to argue against a spherical Earth. Conducted along a straight 6-mile stretch of the Old Bedford River in England, the experiment aimed to observe the curvature of the Earth by measuring the water's surface. In 1838, Samuel Rowbotham, a prominent flat Earth advocate, conducted the initial experiment. He observed a boat with a flag traveling along the river and claimed that the entire boat remained visible throughout the 6-mile stretch, suggesting that the Earth was flat. However, subsequent experiments and refinements provided more accurate and reliable measurements. In the late 19th century, Alfred Russel Wallace, a respected scientist and contemporary of Charles Darwin, reconducted the experiment under more controlled conditions. Wallace used more precise equipment, including a theodolite, a surveying instrument that measures angles with high accuracy. His results confirmed the Earth's curvature, showing that objects disappeared from view as they moved beyond the horizon, consistent with the expected curvature of a spherical Earth. These findings were corroborated by numerous other measurements and observations. Despite its controversial origins, the Bedford Level experiment ultimately provided clear evidence of Earth curvature, demonstrating the importance of rigorous scientific methods and the need to continuously refine and verify experimental results. Thank you for joining us on this journey to uncover the truth about our planet. We've explored historical evidence, scientific proofs, natural phenomena, and crucial experiments that all unequivocally demonstrate that the Earth is a sphere. By understanding the observations of different constellations, the Coriolis effect on weather patterns, the precision of gyroscopes, and more, we hope to have shed light on why the flat Earth theory simply doesn't hold up. Knowledge and curiosity are powerful tools, and we're excited to continue exploring the wonders of our world with you. If you enjoyed this video, don't forget to like, share, and subscribe for more fascinating content. Comment your opinions below. We would love to discuss this topic further with you. Stay curious, stay informed, and until next time, keep looking up.